The goal of our paper is to compose photorealistic scenes from captured images of objects. Neural radiance fields, or NeRF, are highly effective for synthesizing novel views of a scene. However, NeRFs assume static scenes and fixed illumination. They infer the radiance along a ray after all light transport has occurred in a scene. For dynamic scenes where objects and lights can move and the light transport changes, a NeRF would have to be trained separately for every new scene configuration. We propose to decompose the rendering problem into two components, per object light transport and per scene light transport. For each object, we model how light bounces within a single object, such as light bouncing from the seat of a chair to the back of the chair. We approximate this with Object-Centric Neural Scattering Functions, or OSFs. OSF is a learned 7D scattering function that takes as input a spatial location, an incoming light direction, and an outgoing light direction. The function outputs the volumetric density as well as the fraction of light arriving from the incoming direction that scatters in the outgoing direction. OSF is like NeRF, but with two extra input dimensions for the incoming light direction. Because OSF is a radiance transfer function rather than a radiance field, each OSF is intrinsic to its object and independent of the scene it is in. This enables building a library of OSFs that can be reused across different scenes. At the scene level, we model how light bounces between objects, such as light bouncing from a wall to a chair, by integrating our OSFs with volumetric path tracing. Similar to NeRF, we evaluate density and radiance at samples along each primary ray and composite them with an over operator. Unlike NeRF, we estimate the radiance for each sample by integrating over the 2D sphere of incoming light directions. We estimate the integral with Monte Carlo path tracing to reproduce shadows and indirect illumination effects. In the first experiment, we train one model per object and test on novel light conditions for individual objects. We find that OSF is able to predict the appearance of objects accurately, such as shadows on the couch or shadows on the chair, as well as specular details on the ottoman. Next, we compare results on scene composition, where multiple object models are combined into scenes in random pose, lighting, and viewpoint configurations. Not only does our method produce more accurate object appearances, but our method is also able to render shadows cast by objects onto the ground, as well as indirect lighting from the walls. To summarize, we have introduced OSFs, a method for composing scenes from captured images of objects. The key idea is that we decompose a scene into implicit object functions that are reusable across scenes where objects, camera, and lighting can change. Combined with volumetric path tracing, OSFs can be composed into photorealistic scenes with inter-object light transport effects such as shadows and indirect illumination without retraining. Thanks for watching.